It's possible that in a few centuries, humans may be able to capture all the energy on Earth. In a few thousand years, we might be able to capture all the energy from the sun, and we might be able to harvest all the energy from every star in our galaxy in 100,000 to 1 million years. Today I'd like to discuss the Kardashev Scale, and later on in the episode we shall discuss Dyson spheres. Let's begin with the basics. Right up until 1964, there wasn't really a good way of measuring how advanced a civilization was. That's why in 1964, Soviet astronomer Nikolai Kardashev created the Kardashev Scale. The Kardashev Scale is a method or one approach of measuring how technologically advanced a civilization is, based on the amount of energy available to them. When he created this, Kardashev originally only had 3 different categories. A Type 1 civilization, able to harvest the energy output of a planet. A Type 2 civilization, which is able to harvest the energy output of a star. And a Type 3 civilization, a civilization able to harvest the energy output of a galaxy. Kardashev originally only conceived of Type 1, 2 and 3 civilizations, but subsequently some folks have created additional extensions to the scale, Type 4 and 5 civilizations, and we'll discuss these later on in the episode as well. The scale is measured depending on a civilization's total energy output. For Type 1 civilizations, this is 10 to the power of 16 watts. For Type 2 civilizations, this is 10 to the power of 26 watts. And for Type 3 civilizations, this is 10 to the power of 36 watts. Again, this scale classifies civilizations by how much power is available to them. So if your civilization has 10 to the power of 16 watts available to them, it is a Type 1 civilization. Also, it's important to note that the Kardashev scale isn't a uniform scale, because it goes from planetary, solar to galactic. If Type 1 were a grain of sand, Type 2 would be an entire beach, and Type 3 would be all the beaches on Earth. The scale isn't so handy if you want to classify a civilization anything less than a grain of sand. If Kardashev knew that this scale would be used commonly, then I'm sure he would have included mankind and scaled it better. First off, a Type 1 civilization or a planetary civilization can harness the total amount of energy from their home planet. It was said by Carl Sagan that here on Earth we currently are a Type 0.7 civilization, almost a Type 1 civilization. Mankind doesn't even make it onto the Kardashev scale. Now, while it's said that to be a Type 1 civilization, you need to harness all the energy on your home planet. You don't necessarily have to get every single last bit of energy, because that's virtually impossible. Your civilization would be there forever, trying to collect every last gust of wind, creating as many generators as possible to convert every wave and tide to electricity, and every single photon of sunlight that is directed at Earth. No, your civilization just needs to reach 10 to the power of 16 watts in order to be a Type 1 civilization. Storing every bit of energy available on your planet in order to be a Type 1 civilization is not strictly true. And don't be confined to only using the common methods to get energy. You can always use fusion power. In order to be a Type 1 civilization, we would need to convert about 2 kilograms of matter to energy per second. Theoretically, we could do this by fusing about 280 kilograms of hydrogen into helium every second, giving us a rate of about 8.9 times 10 to the power of 9 kilograms per year. But I'd say solar power is one of the most effective and is fairly easy to do, but we shall discuss this when we come on to Dyson spheres. Next on the scale, a Type 2 civilization or a stellar civilization captures the total energy output of their home star. This is where the use of megastructures such as a Dyson sphere is necessary. A Dyson sphere is a hypothetical megastructure that completely surrounds a star, capturing most or all of the available energy from it. It was proposed in 1960 by Freeman Dyson. Dyson originally imagined the Dyson sphere as hundreds or thousands of solar collectors orbiting a star, not a complete sphere. It's understandable because of the name, but whenever I'm discussing Dyson spheres, I'll always be referring to thousands of solar collectors orbiting the Sun, and not the sphere variant. A complete sphere, although has more space and is more effective at collecting sunlight, is virtually impossible. The main reason is because no known material could withstand the exceptional stresses on a structure of such size. Furthermore, it's incredibly unstable. A slight nudge on one side would cause it to fall straight into the sun. It's going to have nudges every 2 seconds because of all the comets and asteroids going around the sun in their highly elliptical orbits. It's a better idea to construct hundreds, if not thousands, of solar collectors and space habitats orbiting the sun. This is called the Dyson swarm, but as I said, the Dyson swarm is what I'm talking about when I'm discussing Dyson spheres. A problem with having thousands of collectors orbiting the sun is that you could be missing out on a lot of sunlight. However, with enough collectors orbiting the sun, you've got this opaque cloud of collectors that captures every bit of sunlight and beaming it back to Earth for us to use, or keeping it for the collectors and space habitats. While the system seems opaque, the collectors are in no danger whatsoever of crashing into each other. 1, because they aren't that close to each other, and 2, because it's not difficult to make sure that each probe knows where every other probe is, knows the trajectory of each probe years ahead, and predict collisions years in advance, and making sure they don't happen. Another problem with having this opaque system is that chances are the probes are going to be occasionally blocking sunlight that would have hit Earth. All you have to do is make sure that none of the collectors' orbiting paths intervene with the sunlight that hits Earth, a kind of patch no zone that the probes never enter, or the probes could just orbit beyond Earth. Of course, this wouldn't be a problem if you only have a few hundred solar collectors in a simple formation such as a Dyson ring. A Dyson ring is fairly self-explanatory, it's simply where all the constructs share the same orbit. But as you get more advanced, you're inevitably going to have formations more complicated, with collectors overlapping each other occasionally. This type of system raises the question, how do you get all the material to build these constructs orbiting the sun? The solar collectors aren't your average Earth solar collector either. These collectors will be at minimum a few kilometers across. What's good about having the collectors instead of a sphere is that you don't need to build it all in one go. You just constantly build more and more collectors and rotating habitats over the course of centuries until you can't fit any more in. You could start off by mass producing them here on Earth, but developing several kilometer wide solar collectors is not an easy thing, at least for us right now. Perhaps by the time we do such a thing, we would be able to do it without a problem, and just mass produce them here on Earth. However, perhaps an easier method would be to disassemble an entire planet for the raw materials. Mercury seems like a pretty good candidate. You could use self-replicating probes, von Neumann probes, to build an army of probes that could cannibalize Mercury and use the matter to make kilometer-long collectors and set them in orbit around the Sun. See the von Neumann probes episode that we covered last week for a more detailed explanation and discussion on self-replicating machines. While the probes are at it, they might as well make a few hundred rotating habitats in preparation for humans to use as living space in the future. Constructing an entire sphere that completely encompasses the sun is a completely different story. If you build it too far out, there's not enough material in the entire solar system to build it, even if it was only a few centimeters thick. Build it too close and it gets too hot for life, electronics, and perhaps the structure itself. As well as the Dyson sphere, there are many other variants. There is the Dyson bubble, a system made up of many independent structures called statites, satellites that stay at the same distance from the sun, using huge thin light sails to stay suspended in space. These constructs would have a perfect balance between the push of radiation and the pull of the sun's gravity. It completely removes the possibility of two crashing into each other since they're stationary. And it doesn't matter at what distance you put your statites. You could have the statites at varying distances, because the relationship between the radiation pressure and the force of gravity from a star is constant regardless of the distance, so long as there is nothing in the way of the star. And like the cloud of solar collectors, you could pretty much cover all the sunlight from the sun with enough statites. Megastructures aren't the only way to achieve a Type 2 status. For instance, you could do star lifting, removing matter from a star to use it for other purposes. Starlifting is often thought as useless and over the top, but actually it's got many benefits. You might want to starlift to get some elements, especially hydrogen, to increase a star's lifetime, to create new stars, to decrease a star's brightness, or even to prevent a star from exploding. In the far future, humans might even use starlifting on the sun in order to stop it from expanding as a red giant. That is, if we haven't colonized a different solar system by then or gone extinct. A more exotic method is to capture energy from a black hole. One way of doing this would be to feed a black hole stellar mass, or mass from a star, into a black hole in order to collect the photons that would be emitted by the accretion disk. Another method would be to just capture the photons already escaping the accretion disk. This reduces angular momentum of the black hole and is known as the Penrose process. Other methods could include somehow collecting the energy of gamma ray bursts, or even the emissions from quasars could possibly be a power source, that is if they're collectible. Last on Kardashev's original scale is a Type 3 civilization, or a galactic civilization. A Type 3 civilization is able to capture all the energy of a galaxy. The methods to achieve Type 3 are just the same as Type 2, but on a larger scale. One way of achieving a Type 3 status would be to put a Dyson sphere or Dyson bubble around every star in your galaxy. Or perhaps you could attain energy from white holes, assuming they exist. See the white holes episode for a more detailed explanation and discussion on white holes. So as mentioned, Type 1 civilizations would harvest all of their energy from their planet, which is about 10 to the power of 16 watts. A Type 2 status is 10 to the power of 26 watts, which is pretty close to our sun's output, and a Type 3 civilization is 10 to the power of 36 watts, just under the Milky Way's output. Famous astronomer Michio Kaku suggested that humans may be a Type 1 civilization in 100 to 200 years, a Type 2 in a few thousand years, and humans might be able to harvest all the energy from every star in our galaxy in 100,000 to 1 million years. I'd say I agree with his predictions for a Type 1 and 2 civilization, but I can't see humans having travelled to each star in the galaxy in less than 1 million years. In the Von Neumann probes video, we discussed that it would take Von Neumann probes a few million years to 10 million years to colonize every planet in the galaxy, and that's not including the time it would take to build each Dyson sphere. Like a lot of topics we discuss on this channel, you can apply them to the Fermi paradox. We could tell if an alien civilization was using a Dyson sphere, for example, because it would produce lots of heat, mostly in the infrared part of the spectrum, and astronomers are trying to detect unusual high amounts of infrared, but with no avail, meaning that they are either really rare or don't exist. The best evidence of a Dyson sphere comes from Tabby's star. In short, the Kepler Space Observatory has been studying about 150,000 stars in a certain region of the Milky Way, and one star in particular showed some very strange dips in its brightness that cannot be explained. There has been additional types suggested to the Kardashev scale, such as a Type 4 civilization, harnessing all the energy from an entire universe, and a Type 5 civilization, harnessing all the energy from several universes. But at that point, it's just astronomers getting imaginative. If we were to take it seriously though, we probably wouldn't recognise a Type 4 or 5 civilization because we've got nothing to compare it to. They would seem like gods to us. Now, while we would seem like ants to them as ants are to humans, that doesn't immediately imply that they wouldn't be interested in us. I get this a lot in comment sections, that more advanced civilizations wouldn't be interested in us. I think they would. Using that analogy, if you had never seen an ant before, but knew there was a possibility that they exist, although unlikely, and you came across one, you'd be pretty interested in them. It would be as exciting as discovering an extinct species. With that being said, I do agree that we would be like ants to them. The Kardashev scale categorizes civilizations going up the way, but physicist John D. Barrow suggested a scale going down the way. This scale categorizes civilizations by how small matter they can control. A Type 1 civilization would be able to control just normal regular matter. A Type 2 civilization would be able to control genes. Type 3 would be able to control molecules. Type 4 would be able to control atoms. Type 5 would be able to control protons. Type 6 would be able to control quarks. And Type 7 would be able to control space-time. Comment down below your thoughts on the Kardashev Scale. Make sure you subscribe for more content on astronomy and futurism. If you enjoyed this video, check out my most recent video, a previous video, or my playlist on the Fermi paradox. Thank you so much for watching. Have a nice day.